Hello again. This video is part 3 of our series on navigating in space. You must know your spacecraft's orientation. Otherwise, any change in velocity caused by rocket motor thrust will be in the wrong direction. If you have telescopes or communications antennas on board, you also need to know which direction these are pointed. Therefore, determining spacecraft orientation is vital for mission operations. Here are some common systems used for this purpose. 1. Star trackers. These are wide-angle cameras that capture images of stars. By comparing star patterns in the images to a database, the spacecraft's orientation can be determined. Some commercial star trackers are capable of measuring spacecraft orientation to an accuracy of less than 1 microradian. 2. Magnetometers. These measure the magnetic field around the spacecraft. By knowing the magnetic field's characteristics in each region of space, the spacecraft's orientation can be estimated. These are useful for near-Earth operations. 3. Sun sensors. These detect the sun's position relative to the spacecraft. Since we know the position of the sun relative to Earth, it's a simple method for orientation determination. 4. Earth horizon sensors. These sensors detect Earth's horizon to determine spacecraft orientation relative to Earth. They are most effective when used in low Earth orbit. 5. Radio frequency receivers. RF antennas can be used to determine spacecraft orientation by tracking signals from Earth or another spacecraft. 6. Inertial measurement units. These units measure angular rates and acceleration for each inertial coordinate axis. These are highly accurate in the short term, but may experience drift over time, requiring periodic calibration. In the image on my left, I show a simple functional diagram of a 6 degrees of freedom IMU. A 9 degrees of freedom IMU would also include a magnetometer for each axis. Spacecraft often use combinations of these methods. For example, they may use IMUs to provide short-term data while using star trackers or sun sensors to correct for IMU drift errors. In the past, IMUs used platforms that were stabilized in inertial space using 3-axis gimbals. These systems kept the accelerometers pointed in fixed inertial space directions regardless of the orientation of the spacecraft. Mechanical gyroscopes were used to measure angle rates, and these signals were fed back to torque motors to counter the rotation. Later, counter-rotating laser beams were used rather than mechanical gyros to measure angle rates. These were smaller and lighter. Many IMUs are now called strapped-down systems because they do not use gimbals to maintain the accelerometers in the inertial axis directions. These simply measure accelerations and angle rates in the spacecraft's body coordinate frame, and these are then transformed into the inertial frame using the most recently calculated orientation angles relative to the inertial frame. Both angle rate and acceleration measurements can now be done using microelectromechanical systems, or MEMS. IMUs based on MEMS technology are very small and lightweight compared to the older systems that use stable platforms with mechanical gyros and strapped-down systems that use laser gyroscopes. An inertial navigation system, or INS, uses the output of the IMU to calculate current position, velocity, and orientation in an inertial frame. Since all these values are calculated by integrating acceleration and angle rate, errors tend to accumulate over time, producing drift that requires other sensors for correction. These other sensors include sun sensors and star trackers. If you find this video useful, please give it a like. If you find this YouTube channel useful and want to be notified when we add more videos, click on the notification bell. Finally, leave a note if you have comments or requests for new videos. Goodbye.